Thanks, Robin. So I hope you hear me well. So thanks a lot for the organizer for the invitation. It's really great to be here and see colleagues and talks and learn. So it's really a great school. So I want to talk today about optical imaging in complex media, which is a title I gave to my presentation. But I added a little bit of I extended the title a bit because I will talk about computational imaging in complex media, because we need a lot of computational tools to perform imaging in complex media. And it's actually connected to some computing with complex media, and I will try to say a little bit about that if time allows. Otherwise, I will probably just squeeze it. Okay, so first, before I start, I really want to acknowledge the team that I am basically co-animating with Hilton Barbosa de Aguiar, who is a CNRS researcher. And many of them are here today. And I really want to acknowledge, because many of the things I'm presenting today is their work, at least not just of the people that are here now, but also all the alumni, PhD and postdoc, of course, the first one being Sébastien, which is the organizer today. So what I want to say is, okay, of course, there is some breaks that you have time after the talks to enjoy the place. But there was last week a special issue of Nature Physics about complex optics, and there was quite a lot of papers, so I just want to point out for those who didn't see it. Many of the authors are in this room, some of the authors at least, and I really want to cover today more or less these two topics. So this one is really the one I wrote about, about imaging. How do I do that? Oops. The one I wrote about imaging and computing, and also there was a very nice article by Jacopo Bertolotti and Ori Katz about imaging. Okay, so imaging through turbulence is one example of weakly scattering medium. So you have a jet engine blowing some hot air, and it's basically perturbating the wave coming from a point. So a point source would give far away a plane wave, but this plane wave would be distorted, and when you put it to a lens to get an image, you get basically an aberrated point spread function here that will basically blur the image. So the solution to that is adaptive optics. What you need to do is take this aberrated wavefront, and in real time, you want to basically measure this wavefront and compensate, actively flatten the wavefront again with an active element that is normally a deformable mirror. And when you do that, you can really go from this blurry PSF to a sharp peaked PSF, and you can recover the image quality. So this is, of course, very important in astronomy, because you can compensate like that the atmosphere perturbation. This is, for instance, there is adaptive optics installed on the Very Large Telescope of ESA. And just to show you the difference, this is Neptune with adaptive optics or without adaptive optics. So you see that there is really a huge gain in correcting these last kilometers of atmosphere that basically blur the image. Another example, of course, is, for instance, when you look larger field of getting much higher resolution and signal from stars. So this is also one of the reasons you want to just get rid of the atmosphere, and there's no adaptive optics on the James Webb Telescope. So it's also important not just in astronomy, but also for instance, imaging of the eye. So this is one example that I like a lot, where you see basically on top, you see the theoretical point spread function of the eye as your pupil open. So at night, of course, your pupil open, and the resolution should increase because you have a larger numerical aperture. But actually, what happens is the resolution decrease because your eye is not a perfect optics, it's not perfectly stigmatic. So what you can do is actually use adaptive optics to correct this aberration, and you can really go from this blurry image of the retina to a sharp image where you can see and count all the photoreceptors. This is actually very important for many diseases like macular degeneration, diabetic retinopathy, where you really want to get these high-resolution images, and it is really used in the medical field. Okay, so what I want to talk about today is, of course, a much more stringent regime of scattering, and we've heard about multiple scattering many, many times. But I just want to remind you this, that with this picture, that you have different regime of scattering. You have ballistic light, so unscattered light. So even though there is a lot of things in between, many photons in this case arrive to your eyes unperturbed. So this is ballistic light. Then you have single scattering. We heard about it just before from Rémi. This is responsible for the blue color of the sky. And the multiple scattering regime in this picture would be the cloud, which is really this white, opaque, diffusive material where light has been scattered many, many times before exiting. So it's important, again, coming back to imaging for tissue imaging, because we are scattering. This is a zoom on the skin, and you can define a typical mean-free path, scattering mean-free path, so about 50 to 100 micron in the visible and near infrared. That's how deep you can go before being scattered. And of course, there is some anisotropy. The light is scattered mostly forward, and you need of the order of 1 millimeter to be fully scattered. Okay, so of course we are scattering, because if we were not scattering, we would look a bit like that, and this would be much easier for imaging purposes, but maybe less nice. So, but this is just to show you what happens if you remove the scattering. So actually, this is a very pathological example of a living animal that is almost transparent, at least of this size, because many, like fish, are quite transparent. But you can actually clear a biological tissue. So you can make it transparent. It's called optical clearing, and there is an example here. It's called clarity. It's a process by which you take, for instance, this brain on the left, and you will basically replace all the water by some kind of high index material without perturbating the rest of the structure. So in this way, here on the right, you still have the brain, but it has been clarified, or it's almost transparent. And that's great, because in this case, you can get some really high resolution images without being just with ballistic light. Okay. Unfortunately, it's a very destructive process. Of course, you replace all the water by some polymer, and it's and it's really high index polymer. So it's really not good to do live imaging. But if you want just to see the structure, it's okay. And I just want to show some nice images obtained of a clarified brain. So this is really the scale. You can see the scale, but it's about several millimeters. So it's like 2 or 3 millimeters. And you can really see in depth. Then you have to do some kind of light sheet microscopy for the experts. But you can really get this high resolution image all across this diffusive material once you've clarified it. Okay, so really with, and importantly, with optical resolution. Okay, so if you try to now, assuming that you can't clarify the brain, you can't clarify your object. You want to see, you want to do some imaging, but you have scattering, okay? And you can basically, you have to deal with ballistic light. So you want to select these few ballistic photons that have not been scattered. And there are many, many techniques that allows to do that. And somehow you can really put them all in this graph. So this is the penetration depth in terms of transport mean-free path. And this is the resolution. So the general idea is you can do very high resolution microscopy here. So you no need to go into the detail of what each acronym means. And you will get high resolution, but you will get to basically a few mean-free paths at best. Okay, and then you have also some more mesoscopic imaging technique with diffuse optics, or you can also change type of wave, go to acoustics, and then you can go much deeper, but then you will lose in resolution. So typically, you have this kind of trend that the resolution is linked to the depth, and the regime of interest would really be, to go there, okay, where you have at the same time high resolution. I mean, at least in this regime, don't need to be really sub-wavelengths, but some high resolution, optical resolution, wavelength resolution, and still go very deep. Okay, but that's hard, and maybe the take-home message is seeing in tissues in vivo at depth remains an excessively difficult problem. So you have to go back a little bit to physics to try to see what you can do, and this is what I will try to show you during this talk. So we'd like to simplify. So of course, we don't want to take a biological tissue to do our physics experiments. So what we do is, this is typically the things we work with. So this is as good as it gets as a biological media for physicists. It's just white paint. So to some extent, we can study already a lot. So it's really made of this aggregated particle like we saw before, typically with not much order, because if you let it dry, they will get very stable, but they will still be very disordered and with a lot of transport mean free paths. Okay, so I stole some pictures from my colleague Emmanuel Bossy, now in Grenoble, to show a little bit the physics of what happens when you have a disordered medium and you have scattering. So this is a wave coming from the left, and the wave encounters some diffusers. So each time a diffuser is encountered, there is a spherical wave that is emitted because it's very small. And you can distinguish maybe some secondary scattering events when the light from the wave from one diffuser bump on another one. Okay, so that's really basically what you see here. The ballistic wave was basically almost unperturbated, but you have this secondary wave with some the single scattering events and very few second order scattering events. So of course, if you take now this white pane that I was showing you before, things get much more complex, and you can't really assume there is just a single scattering event on average. There is much more than that. And what happened then is shown in this nice simulation. So now the pulse arrives, and you will see the ballistic light will very quickly completely disappear. Okay, so there is an exponential attenuation. It's gone now. There's no more ballistic light, and there is just scattered light propagating inside the diffusive material. Most of the light is reflected, a little bit of the light is transmitted, and there is really very strong spatial and temporal perturbation. But the key point, and I think we've heard about it, I mean, mostly from also a lot from Matthias at the beginning of the week, that there is still coherence, there is still possibility to manipulate this and to play with these interferences. Okay, so what you see if you put a camera on the far side, and again, this is something that we've seen a few times, it is a speckle pattern, intensity speckle pattern, so not second order speckle pattern. And each speckle grain can be seen as a sum of many, many different paths. And because of the scattering process, each path has a phase that is basically anywhere between 0 and 2 pi. So you basically have a sum of random phasors, and this gives you the statistics of the intensity. And also the size of the speckle grain is given by the numerical aperture in this particular plane where you observe the speckle. So if you're really close to the diffuser, the angle is very large, the speckle is very small. If you're far, the speckle grains tends to become bigger. Okay, it's in 3D, so I was showing you 2D picture, but in 3D, of course, polarization gets randomly rotated at each scattering event. I mean, after a few scattering events, it becomes completely random, which means that you can see the speckle that you see on a camera as a sum of two orthogonally polarized speckles, which are completely uncorrelated. Okay, and of course, this interference is very much wavelength dependent. So the longer the light stays in the medium, the more sensitive it is to a change of wavelengths. So you can show that the speckle depends on the wavelengths, and this spectral dependence is inversely proportional to the dwell time of the light inside the medium. And of course, the take-home message that I will try to, the red thread of my talk, will be that even though it is a very complex phenomenon, it's a deterministic and controllable process, and you can manipulate this speckle with basically control of the wavefront, which is just adaptive optics. So of course, there is a lot of work that has been done in acoustics, and many of the things we do is heavily inspired from the work of Matthias Fink and the Langevin Institute, where you really benefit from the linearity and the reversibility of the wave equation. And you know that if you have a point source and you record many diffusers, and now you play back in reverse, you will refocus in space and time on your source. Okay, so this is beautiful. But of course, in optics, we don't have the possibility. This is not this point source, and also these detectors are not easy to get by. So we need to basically play different tricks in order to play with the same physics in this wave domain. So what we play with is basically shaping tool. And I just want to really show the three main class of things we are using, although there are a lot more exotic approaches. So the first one is deformable mirror. So it's really what I was showing you at the beginning for adaptive optics. It's just a few actuators. They are very fast because they were made to correct the atmosphere that is changing very fast. They are super expensive, so they really cost a lot, and they are really big, and you can, that's really typically hundreds of thousands to millions of euros to to have a full system. What we use a lot is a special light modulator. So it's basically arrays of pixels. So now you have typically hundreds of thousands or millions of pixels. And each pixel, you can basically change the liquid crystal phase in order to change the phase of the reflected light. You change the index of refraction, and you get a delay. And with that, you can get 2 pi phase modulation. It's typically a bit slow, so typically a few tens to hundreds of hertz, because it's really linked to the physical rotation and the physical reorientation of the liquid crystal. That's still really the main tool we are using. And the last one we can use is also MEMS. So, and one of them is this DLP from Texas Instruments, which is basically this display technology that is used in cinemas and even here. And it's really many pixels that you can turn on and off. So they can just rotate between 2 positions, either transmit or not transmit. Okay? And by switching them very quickly, you can encode any gray level you want. So with that, it's actually very nice and super cheap. One problem is you can't really directly control the wavefront, so you need to basically play some tricks in order to do some wavefront shaping in a more efficient way. So a typical experimental setup, this is a setup from that we had in our lab more than 10 years ago at Institut Langevin, but that basically is very similar to most of the setup around the world. You basically have a laser. This laser will shine on a wavefront modulator. This one is not, I will show it a bit later what it is. And we shine through a scattering medium, for instance, a layer of white paint on a glass slide, so just dropping and letting it dry with some particles. And then on the far side, you want to put a detector or a camera, which is what we have in optics, to measure the intensity. And well, I mean, it's I think many in the audience have seen this picture already, but I think some may not, because it's there is a very wide audience. And I still really want to point out this absolutely seminal paper from Allard Mosk and Ivo Velkup, where what they did was exactly using this technology of spatial light modulator. And they take this, if they send a plane wave through the scattering medium, they will get a speckle. And what they did was putting a detector and optimizing the wavefront with some feedback loop in order to maximize the intensity at the detector position. And they obtained this extremely striking result that they didn't get a small enhancement, they get a huge enhancement. They basically get a very strong focus, 1,000 times brighter than the background, which was basically diffraction limited. And you can see it as some kind of extreme adaptive optics. So let me just walk you through what exactly happened. And this is some simulation that Thomas Shane, one of my first PhD students, did. You have the wavefront, and what you try to do is you try to maximize intensity in the center. Okay. What you try to do, you play with the phase of every pixel, and you keep the value that maximizes the intensity. And what you do is you make this particular pixel interfere with the average field at this position, and this basically corresponds to aligning these different phasors that are initially completely random relative to each other all together. And in this case, what you get is you get really this very sharp focus. The total intensity is basically proportional to how many pixels you play with, because the more pixels, you kind of go from square root of n average distance from the origin in terms of sum of random phasors to n. So you have this, in intensity, you have this n to n square. So you have a factor n of gain in intensity. And one important point is also that the speckle is really has very short-range correlation, which is really the size of the grain. So whenever you get this constructive interference at this particular position, you know from the multiple scattering process that there shouldn't be any, the focus should be really localized to this particular grain that is diffraction limited. Of course, this comes with a lot of caveats from mesoscopic physics, but at least in first approximation, that's a very good assumption. So you get this very sharp focus. Okay. Okay. So this is valid because I assume that my system is absolutely static. But I want to. We have to keep in mind when we do the physics the limitation of what is the end goal. And I really want to remind you that tissues are decorrelating. They are moving. They are not just fixed. And I can show you, for instance, these two measurements that were done. I think 7 years ago, 6 years ago, in Chang Wei Yang's group, and they were looking at the correlation of the speckle over time of light going through a tissue. And you can really see that in vivo, for instance, in this case, they had a very fast decorrelation and then some kind of stable plateau of correlation of speckle. And it was really due to the blood flows and then also the heartbeat, etc., etc. So you have all the movement of the body that will affect the speckle stability, and you cannot assume that the system is stable. Even ex vivo, so you get much better stability, like of the order of a few seconds or tens of seconds, as a function of the thicker the medium, of course, the more sensitive it is to a decorrelation. But this gives you the range of stability of in vivo and ex vivo tissue, and that's what you have to. That's the time you have in order to perform this kind of experiment. So one way to do it faster than optimization was actually introduced about the same time. It's basically optical phase conjugation, digital optical phase conjugation. It has the advantage of being an almost instantaneous process. You don't have a long iteration to do. What you need to do is measure on a sensor the interference of the speckle that comes out of your medium with some kind of reference beam, a plane wave, to record a hologram. And then this hologram, you can basically send it back to the SLM with some minimal treatment, modification. And then the same plane wave will basically diffract of this hologram that you just display. And if you do it well, you can basically emit the so-called phase conjugate of the light beam that will basically then be the equivalent of a time reversal operation, but on monochromatic waves. So this is one way to do relatively fast some scattering compensation. And for instance, in this paper, they were really showing that they can really, if they repeat this optical phase conjugation over and over again, they can do it in about a millisecond. They can really maintain a focus even though the system is decorrelating over time. It's kind of a repetitive process, but it works. The approach we took in our group was to try to do some optimization or and just to use a faster modulator. So we actually played with this so-called Boston micromachine modulator that is basically a MEMS. So each pixel now can play with it's like a very fast adaptive optic. So it's basically a small pixel about 300 micron across. So you have 32 by 32, and you can go about 10 kilohertz. So it's much faster than the liquid crystal SLM. And in this case, we had to basically play a lot of tricks in terms of fast feedback, FPGA controller being as fast as possible. And we could really optimize at about 10 kilohertz, which is quite a feat electronically speaking. So it was really the work of Baptiste Blocher, PhD student. And what we had was the following, just to show you that it's possible, at least in principle. We had a medium that was really decorrelating over time, so some kind of colloids suspension of particle. And you can see that the speckle is changing over time. It's a real-time movie. And when you turn on the optimization, that's when the green square appear, you can get a focus. But of course, as soon as you stop the optimization, the focus just disappears immediately because of disorder change. So it's possible. That's for optimization. So the approach that we implemented 12 years ago during the PhD of Sébastien Popov was really this transmission matrix approach that we've heard about a few times already, where you really have to say that, okay, I have my SLM, it's an array of input pixels. I have my complex system that remains a linear system for the wave, and I have my camera that is also an array of pixels. So I can describe this system as with a linear relation. So I can write a transmission matrix linking the input to the output pixels for the fields, and which is kind of can be extracted from the Green's function or the S matrix, basically of the system on this pixelated basis that are my input and output modes that I can control. So the trick was to measure this transmission matrix. And we did it by basically shining a series of patterns on the SLM. So the idea is to send many patterns, ideally describing a basis. So we use this Hadamard basis that is really nice because it's just 0 and pi phase shift. And when you send them one by one, for each of them, you can record on the camera a speckle. And you have to do some kind of holographic measurement. So you have some kind of reference wave in order to extract the field. And then the first input pattern will give you one speckle. And this speckle will be one column of the transmission matrix. And then one by one, you can measure this transmission matrix in the computer, and as you can see, because of the scattering process, it looks very random. Okay, so so what that was the initial work, but of course we refined it quite a lot. And I just want to point out that random phases, you don't need to send a basis. You can send a random pattern. You can send binary patterns. That's okay. You can just do measurement, intensity measurement. Then you need to do some kind of phase retrieval. This was a very nice work with Angélique that we'll talk about that on Friday. So you can simplify this measurement quite a lot to extract the transmission matrix. So once you have the transmission matrix, what you can do is, for instance, focus light. So you can calculate the input pattern that will give you a given output pattern. This is basically what you have to do is display the transpose conjugate of the matrix, which is this phase conjugation operation technically, and then the target that you want. And for instance, with that, you can basically get focus to any position, any detector any pixel that you want, or even multiple ones. And we can play also with different shape of point spread function. That's something we did much later. You can also do the inverse problem. So the goal in this case is to go from the speckle that you measure on the camera in amplitude and field or phase to the input pattern, so to guess what was behind the scattering medium from the speckle that you have and the knowledge of the transmission matrix. So in this case, you have multiple issues. It's actually an harder problem. So you need to do regularization in your inversion in order to recover the input pattern. If you have some priors, you can do some compressed sensing, for instance, on the sparsity of the medium. If you measure just intensity, you need to do phase retrieval, etc., etc. But it's possible, and I'm just putting two references here. It's important also to point out that there is quite a nice branching of this field, not just to paint and disordered medium like disordered system, but also multimode fibers that mix light in a relatively complex way. It has a large number of modes, and because of the dephasing between the modes, you can consider it up to a certain approximation as a complex medium. Not that complex, actually, so people realize it's less and less complex, but still, you get some speckle if you don't take any particular care. And this is important both for imaging, so endoscopic imaging, but also in telecommunication and quantum optics. Okay, so one thing I also want to point out, just for completeness, is that you can extend this transmission matrix approach not just to monochromatic light, one wavelength, but multiple wavelengths, and then you can basically understand and control a broadband pulse, a short pulse. Okay, what we did was introducing the so-called multispectral transmission matrix, where we measure the transmission matrix for different wavelengths. You can actually do it also equivalently a time resolve transmission matrix, where you measure the transmission matrix at a given arrival time, and then you can change this time, and you can get this so-called time resolve measurements. And they are just related by Fourier transform. We also add a third method, which is called the broadband transmission matrix, where you basically measure everything together by just squeezing them and into a single measurement. So what you can do if you play with this multispectral transmission matrix, you can go beyond just spatial focusing, and you can also control temporally or spectrally a focus. So you can choose to focus one wavelength or another. What you can do also is basically control the spectral phase of a focus. And if you make a broadband focusing and you control the spectral phase of the focus, you basically control the time. And for instance, in this paper, the blue curve is the overall intensity distribution on average of a pulse spread by the medium. And when we control the pulse, we can basically recompress it back to its initial Fourier duration by focusing and making sure that every spectral component is in phase. And this could be important for instance, for multi-photon excitation, two-photon fluorescence, etc. Okay, so the take-home message is, at least on the transmission matrix, is the following: is that you can measure the transmission matrix, and if you can do that, you enter this so-called information age, and it will bring me now to my computational part, because for information you need computation. And if you have this piece of sugar, for instance, and you measure this transmission matrix, well, you have something that is very similar to this lens here that is just described by this 2x2 transmission matrix with one parameter in the paraxial approximation. So you can basically turn this piece of sugar into a lens. This is what I was basically showing you until now. But you can do much more, and you can do many different optical elements. You can make it a very high numerical lens by really going to a place where the speckle is very small, or even sub-wavelengths, if you're really at the surface and you have an evanescent component. You can make it a polarizer by controlling the different polarization. You can make it a spectral filter by focusing one wavelength or another. You can make it even a beam splitter cube and even a circuit. And actually, you can also make any combination of those. So any linear optical element or any linear optical system can be emulated with some accuracy with this kind of approach. Okay, what I want to point out, and this is, I was talking about transmission matrix, but of course everything that I'm telling you is also valid to a large extent in reflection. So this is so-called the reflection matrix, and I think Alexandre will really cover that extensively in his talk, so I won't cover it today. Okay. So why is it interesting for imaging? Well, first, it's called lensless imaging through the scattering medium, because as pointed out in this paper, the focusing, the resolution is basically given by the scattering medium and not by the whatever optical element you have before. So the lens become irrelevant in a way, and the medium become the lens. The other point that I think is worth pointing is you can go a little bit beyond focusing. So if the medium is thin, you have the so-called memory effect that tells you that changing the incident angle would just basically translate the speckle at a distance. So this kind of correlation of the speckle is very useful because it means that you can translate speckle or translate a focus. And this is at the basis of many imaging techniques that will come later on, and I'll try to cover some of them. So it has been generalized also to beyond this angular memory effect to many other memory effects that allows you to do imaging in different scenarios. Okay, so another point is I was telling you how to go through something, and it's important to go inside scattering tissue. I mean, going through is kind of cheating, or it's only useful in some scenario, but for imaging deep in tissue, you want to do it, and you want to basically guide light inside the scattering medium and as non-invasively as possible. So you want to find a way to guide light there, and what you need is a guide star. Just like in astronomy, you want a way to monitor the intensity or the field inside. And in this review from 2015, they kind of cover the different approach that can be taken. So fluorescence, nonlinear fluorescence, ultrasound, photoacoustics, acousto-optics, coherence gating, etc. So you can read all of them here. You can see that they all have different kind of resolution. Some are invasive, some are non-invasive. Some allows to translate the position, some do not. And they have also, some are very slow, some are very fast. So in a way, I think the take-home message is there are many, many techniques to try to guide light inside, but there is no silver bullet. It's not like one of them is winning and it's clear that this is the way to go. It's still very much exploratory how to go very deep. And I think that there's a few more since then, but they remain more or less, this list remains relatively accurate to date. One example I want to show is some work we did with Ori, Mathias, and François Ramaz in Institut Langevin, which was to use acousto-optics in order to go beyond this transmission matrix. So what Ori proposed and performed was really nice. So this is a transmission matrix that normally goes from the SLM to the camera, and this is really with the same frequency. But now if you add an acoustic focus, well, this acoustic focus will shift coherently some light, and you can record speckle at the laser frequency plus the ultrasound frequency, and you can make some kind of holography of that to measure this component only at the shifted frequency. And if you do that, what you can do is you can basically get the so-called acousto-optic transmission matrix that will tell you about the light that has been basically exploring this particular position. And with this information, you can actually go back and refocus or extract some information about this position. So this is one way to, for instance, use acousto-optics for the transmission matrix. What I want to talk about, So what I want to talk about more today is the so-called, is another contrast mechanism, so fluorescence, linear fluorescence. And this is some image of basically of so-called brain bow. So it's basically imaging of neurons, and each neuron is tagged by a different combination of fluorophore, which allow you to really get some super nice images of neuronal population. So it's I like this movie very much, but I think I really want to point out that fluorescence remain in imaging extremely popular. So it still remains to date the most popular way to do some optical imaging in biological tissue, and really it's still not in the GuideStar catalog that I was listing before, and I will explain why. And so we really try to explore, and I will try to walk you through some of the work we did, fluorescence as a way to do some imaging in tissue, because it's so widespread, and also there is so much light. So fluorescence actually very nice. You typically have a lot of signal compared to second order or third order fluorescence, for instance. So why is it not a good guide star? And actually, if you look at this paper, was really from 2008 from Allard and Mosk and Ivo again, and they tried to basically explore exactly that. So what they did was they took a laser, they shine on a sample, and they collect the fluorescent light emitted by this sample on a very sensitive CCD camera. And this sample is basically scattering, but there is one fluorescent bead in there. Okay, so what they do is they start from this fluorescent pattern here on the EMCCD with a plane wave. They optimize a total fluorescence, and what they got was a much brighter diffusive spot in their camera for this particular wavefront, and they knew that they basically focus on this bead because they had only one. Okay, so with one fluorescent bead, you can really get a focus with fluorescence. The problem is, as soon as you have an extended object or multiple bead or high density of bead, it doesn't work anymore because basically the optimization will tend to focus on all beads rather than on a single one. So it's not good enough. So one solution was actually proposed by Ori and others to really use nonlinear feedback, so two-photon fluorescence. And if you use the two-photon signal as a way to optimize, you will tend to get a single focus. So that's a solution, but of course there is much less signal. You need to use expensive laser and so on. So that's a nice way, but yeah, it was done already. So another approach is to try to unscramble this scattered light, and this was proposed by Jacopo Bertolotti and Allard Mosk, which was to say that if I have some fluorescent object behind a scattering medium and I have some memory effect, I can show that from this speckle blur, so this fluorescence blur here, I can extract the object. Okay, without any shaping, just computationally. And I just want to really briefly walk you through the approach and with this follow-up paper that we did with Ori and Mathias in Institut d'Angers. So what we did was basically saying, okay, we have an object, fluorescent object, illuminated by a narrow band light, by some incoherent light, and then the light will from this object will go through the imaging system, and I will get this blurry image. The general idea is that from the incoherent imaging image formation model, you can write the intensity on the camera as the object convoluted by the PSF. Except that the problem is now the PSF is a speckle. So, but because of if there is memory effect, if the medium is thin enough, it's really the PSF for every point is just a shifted speckle. So you can write this object as a convolution of this object by this speckle, and the general idea is to use this very nice property of convolution, that the autocorrelation of the image is basically the autocorrelation of the object times the autocorrelation of the speckle. And then there is this beautiful property that even though the speckle is very broad and extended, it has no spatial correlation, so very narrow spatial correlation. So the autocorrelation of the speckle is a very peaked function. So it looks, so in a way, the autocorrelation of the image and the autocorrelation of the object are the same, even though they look very different. Okay, and then what you can use is you can use phase retrieval to, from this autocorrelation, retrieve the object. So that's the general idea, and with that you can do it very quickly just with a camera, and this is what we did. So for instance, this is the speckle that we collect with just a mobile phone, taking a picture of the of the speckle coming to the camera, and the autocorrelation of the speckle give you that, and with the phase retrieval you can retrieve this, and this was the original object, and we could play with this in many ways, and it has plenty of nice features. It's single shot, it's diffraction limited, you have no clue how far your object is behind your scattering medium, so there is some pros and cons, but it's what I really like about it, it's how simple it is, because it's just taking a single image, a single frame with a camera. I need to point out that we do leverage also knowledge from not just from acoustics but also astronomy, and this was actually very much inspired by stellar interferometry. So in this technique was invented by Antoine Labeyrie, who was a famous French astronomer, and he was basically looking at stars through the atmosphere, and he was basically getting this highly fluctuating speckle pattern that he couldn't make sense of. But if you take many short exposure and you do the autocorrelation, you can see that from this autocorrelation you get these things, and you can distinguish that it was basically 2 stars, okay, from the autocorrelation of this fluctuating speckle. So what we did is basically, this is really time and space fluctuation, and we did it just with spatial averaging on a single frame with many more pixels. Okay, so but it's essentially the same thing. Okay, so this was a while ago, and what we've been working on in the last few years is really to try to go back a bit more to wavefront shaping, and what we want to go back is really to the fundamental question is, okay, speckle is really something that is a coherent phenomenon. But do we still have some speckle if we have an incoherent object? And the question is, the answer is actually that we still get some speckle even if the object is incoherent and is relatively extended. And the reason is the following. So let me walk you through this. So we have light shining through a medium, and we have a fluorescent bead. And this fluorescent bead will emit some fluorescence that I can collect on the camera. So if I have just one bead, I will have a speckle, and it's basically fully coherent. Okay, so I have a high contrast speckle. The contrast is 1. If I now have a second bead, the contrast will drop a little bit, because what I'm doing is I'm summing in intensity these 2 speckle patterns. So the speckle drop, and so on and so forth. Okay, so this is how the coherent speckle turn to a diffusive and incoherent halo. But the nice point is that this addition of intensities and this loss of contrast of the speckle actually goes only as square root of n. This is really well known, where n is a number of sources. This is well known from this fundamental paper on speckle, and it's actually very good because square root of n is actually quite slow. So and also speckle is highly contrasted. It has high fluctuation. So even though my speckle is reducing with the complexity of the object, even an extended fluorescent object will have some speckle fluctuation. And this is something that we would like to exploit for what I will show you now for imaging. So the first thing we did was, during the thesis of Antoine Boniface, we said, okay, now we have this extended fluorescent object, so the thing that doesn't work if you optimize the total intensity. This is the speckle that we see on the camera, and if we optimize the total intensity, it doesn't work. So can we focus on a single bead even in this case? Can we try to adapt this optimization method that I was showing you before, but to this extended fluorescent object? And the solution we came up with was to optimize not the intensity, but the variance of the image. So we collect an image, and the variance is basically the product of 2 terms. The variance is basically the intensity of the image times the contrast, or you can say that the contrast is the variance divided by the intensity. Okay. So if you optimize the variance, now you optimize these 2 terms in parallel. Okay, and reducing optimizing the intensity and the contrast will tend to focus on as few targets as possible and as bright as possible. And it works, so we could show that with that we could really get enhancement of the contrast. This is the contrast enhancement, and this is the result. We have a camera on the far side that allows us to look at exactly what we are doing, and we can see that starting from this solution of bead, every time we optimize, we focus always on a single bead. Okay, which was nice, at least for optimization. But this is not, focusing is nice, but imaging is better, so we try to optimize of that. But let me show you first something that we did, which was to try to exploit also this principle of low contrast speckle to do some information extraction without imaging. And what we try to really tap into is a different type of imaging. So imaging, what I was showing you until now, was structural imaging. You want to see the structure. You want to see the shape of the object. But what you can do is what is called also functional imaging, where you try to see the activity that is taking place into a sample. And this is particularly important for neuroscience. And in this movie, it's basically a zebrafish, so it's a very small fish that you can genetically modify so that whenever a neuron activates, the neuron will become fluorescent. Okay, so what you are seeing in this case is basically the neurons' activity. So the neurons are basically activating and talking to each other. And this is really the way you do it's a beautiful tool to understand the brain behavior. So it's perfect, but the zebrafish is actually transparent. So if you want to go to more complex animal, you can have these fluorescent neurons, these optogenetically modified animals, but getting the activity is harder. So what you can do is so-called functional, wide field functional imaging, where if the neurons are close to the surface in a scattering sample, like in the brain, you can still, they will give a blob, or you have a little bit of ballistic component that you can recover, and you can get the activity of this neuron. It works with some ballistic. You can use some light field microscopy. You can do some different tricks in order to recover the activity of these neurons. The question is, what happens if now the neurons are in the scattering regime, if they are very deep? Okay. In this case, each neuron will basically they will blink, but what you will collect is just a speckle that will fluctuate. And the question is, okay, this low coherent speckle from this extended, it's because a neuron is 10 microns, so it's much larger than the wavelengths. Can you still get some activity from that? And what we try to do is just retrieve the temporal activity. And the key is that the information is, again, not lost, it's just mixed, okay? So the light from this fluorescent source has been going through the scattering medium and will give basically a speckle that will fluctuate relative to each other, okay? And the key is, can we still separate them? And this was the work of a postdoc, Claudio Moretti, that recently left. You can really model the video that you record as some kind of sum of sources going through some transmission matrix that you don't know, with some temporal activity, some noise, etc. So we did this proof of principle experiment where we basically have beads below a skull. So the skull is very scattering, you can see it here. And the fluorescent beads are 10 microns, so same size as a neuron. And we excite them from below with some temporal codes. So we use a DMD in order to excite this fake neuron with some temporal activity. And then we collect the light that goes through the skull with an SCMOS camera, so a sensitive camera. So all in all, if this was really an observation, if you think of it as in the final experiment, this is just bright field microscopy. It's very, very simple. And so this is what we record. And the question is, can we go back to the activity? And the answer is yes, and I will try to walk you through the process. And again, there you really need a computational approach. So what we did was to say that we have fluctuating sources. So I have to credit Jacopo Bertolotti, who did a beautiful animation of that. So if you have basically this source that turn on one by one, you can let me walk you back to this. So you have each source has a given speckle with some contrast, okay, and they fluctuate in time because of the activity that you're exciting them with, okay. So now if they blink a bit more, then you will just get linear combination of them in time, and what you can do is record basically a movie of this activity, okay. So you have a movie that is basically a data set of position and time. Intensity as a function of position and time. And the key insight is that you can actually factorize this information, that is this video, this space and time data set, into a product of two matrices, which are both very thin and positive. Okay? So one is really the fingerprint, the speckle pattern from each source, and one will be the temporal activity. Okay, and there is this very powerful non-negative matrix factorization that allows you to get this decomposition very well, and with quite a resilience to noise. And now the dimension of of these matrices is just a number of sources, which is much smaller than the number of pixels and frames. Okay, so basically you want to take this movie, and I'm again grateful to Jacopo for the animation. You take this movie and you factor it into two small matrices, one being all the fingerprint from each emitter, and one being the temporal activity. So we did that, and it worked quite well. So this is the time trace. This is the ground truth that we send on the neurons, and we could really recover this activity from this demixing. And we could also check that the fingerprint were actually well correlated with the ground truth, because we can excite them one by one and make sure that it's correlated. So the next step is really to go to real neuron in vivo, and there is a lot of difficulties to do that. And we do that in collaboration with colleagues in the US who are really doing in vivo imaging. What I can show you in one slide is that we try now to improve, and by adding the localization. So the general idea is, if you have these neurons and you record this speckle, well, the correlation between this fingerprint, if there is some memory effect, may give you their relative position. And in this case, we could really retrieve, by correlating this speckle, the relative position between these neurons relatively accurately. So this is encouraging. Okay, so going a bit beyond, we try to do now, we go back to structural imaging, try to see an object, the structure of an object, but exploiting the same tools. So we have basically CW light, so we can shape the incident light, and we have fluorescent beads that are a fluorescent object that is hidden behind a scattering medium. So in a way, you can think of this as a black box, and you have some kind of input by which you can interrogate your system, and you have some output that is whatever you collect on your camera. And the question is, okay, now with that, can you basically find your object? And this black box is basically not really a black box. You actually can make some assumption on what happens. You have a forward transmission matrix for the excitation that we note T. This transmission matrix will excite the bead. It's fluorescent, so it's proportional to the intensity. And then this intensity will basically incoherently propagate back. So now you have an incoherent transmission matrix that is for each point a different intensity speckle that we note W. And we can write an image formation model that the intensity of the camera is W, so this intensity transmission matrix, times the modulus square of my excitation, so T times E in. Okay? So with that, I can play a bit more, and I will try to show you how we can both measure non-invasively these two matrices and try to image and focus on the object. So what we did was sending many random patterns with the spatial light modulator. For each of these random patterns, we measure intensity speckle on the camera. So low contrast, because it's, of course, I'm always exciting multiple beads. Okay? So the first part is to play the same trick as before, the non-negative matrix factorization. So I'm basically factoring this movie, I'm reshaping, so it's space and time, and I'm reshaping into this fingerprint from each bead times the temporal excitation. So if I have this, I know the transmission matrix, I get W, and I also get the excitation pattern. So if I get the excitation pattern, it is as if I had a detector on each of my beads. So I can now, from this intensity for each emission pattern, I can play a phase retrieval step and retrieve my forward transmission matrix from this intensity measurement that were in this temporal excitation intensity. And with that, I can verify that knowing my transmission matrix, I can actually focus, and I have a camera also on the far side to monitor that I'm doing this well, and I can get the focus on each bead. And from the correlation between the fingerprints, again, I can retrieve the position between the different beads, and I can, from that, retrieve the shape of my object. So what is interesting is there is a finite memory effect, so the system is not very thin, so I can really only locate beads if they are within the memory effect, okay, of each other. then I have some correlation between them. But what I can do is by near neighbor, I can find my extended object even beyond the memory effect by combining the information from all these pairs of bits, and this way we could really reconstruct an extended object beyond the memory effect. So it's good, but it's just bits. So the one question is, does it still work if it's an extended object and a continuous object? And this was not at all obvious, but it turned out to be pretty robust. And so the PhD student Antoine, told me, okay, I will try, and he tried, and then he showed me the result, and it was working relatively well. So, for instance, this is some pollen seed that are fluorescent stained. So they are. This is what you get with a bright field microscope, and when you do the reconstruction, you get something like this. So when this is another one, and you can see they resemble somehow the objects. It was actually encouraging enough and good enough to publish. But of course, you need a little bit of faith in what you're doing to see some resemblance between the top and the bottom line. So we tried to improve on that, and actually we could simplify quite significantly the setup and do it without an SLM. So what we did is now, what we just need is to have a fluctuating illumination. And this fluctuating illumination, you don't need an SLM. You can just do it with a rotating diffuser. Okay, and with this rotating diffuser, we basically get a random illumination of our object, and this random illumination will result in this fluctuating speckle. But we don't really need this forward transmission matrix unless we want to focus. So with that, we can have the return transmission matrix and get all the imaging we need. So we did exactly this, and we could really recover the position from every bead, and from this get some nice reconstruction of our beads just with a rotating diffuser. And what's actually nice is also the student Lei Zhu improved a lot about this cross correlation by doing, instead of doing cross correlation, he did cross deconvolution. And this turned out to improve a lot the reconstruction, and we could really get some pretty nice reconstruction. Again, well beyond the memory effect, and more importantly, it worked really well for also continuous objects. And you don't need that many patterns. So this is just to show you that you don't need thousands of patterns, just with a few hundreds of patterns, which you can get very quickly with a rotating diffuser. You're not limited by the speed of the SLM. You can get some decent reconstruction of your initial object. Of course, as you increase the number of patterns, it gets better and better, but you can choose to stay if you have some stability or some time of measurement. Even a few patterns allow you to get some decent images. And we could really get some much better image reconstruction. So now you can see that you don't need so much face to be convinced that the imaging is okay. So yeah, this was of course a nice improvement over the previous work. Okay, so I want to now go back a little bit to computing and try to explain to you why there was no machine learning so far, just signal processing and related method, but there was no machine learning yet. But I will try to convince you that it's still interesting to do a little bit of machine learning, because matrix machine learning, as you know, is layer after layer of neural networks, and each layer you can see it as a matrix multiplication. So what our machine does is actually, optically, we are making matrix multiplication in another analog way. So there has been quite a lot of work in trying to use these neural networks in order to image through scattering media. And I want to point out these two, which are basically from Alex Turpin, I think he was in Glasgow at the time. And what they did is they say, okay, I have a certain number of input, I have a certain number of output, so SLM and camera. Can I now train a neural network in order to predict my output from my input? So he made this convolutional neural network, and he trained the network, and after training the network was able to say, okay, for this given pattern, I will get this particular output speckle. And if you do that, you can use the same network, say, okay, now I want to focus at a given point, what is the input that I need to send? And it worked more or less. Okay, so it worked more or less, and I think the reason it worked, but only more or less, is because they didn't really care to adjust the properties of the media of the network to the physics problem at hand. Okay, so this convolutional neural network is more for image analysis, but it's not really, it has no relation whatsoever to the physics at hand. There was this, a bit later, it was still very nice and early, but a bit later there was this really nice work by Daniele Faccio and Roderick Murray-Smith. So Daniele is more the optics guy and Roderick is more the machine learning guy. And they did exactly the same idea. So they have basically now a multi-mode fiber. They can send pattern and they can measure image on the camera. But now what they say is, okay, instead of making a multi-layer neural network, why not try to do it a bit smarter? The system is basically one complicated matrix and a nonlinearity at the modulus square. So let's now look for a one-layer neural network with complex coefficient, because the coefficient of the transmission matrix are complex, and train this matrix, this neural network, to mimic my input. And they got, it worked very well, so the network is much simpler, and it worked very well. It can also focus, and it can generalize very well. So it really works well beyond the training they used to train the network, which was not really the case for this one. So I think this is a nice approach that we try to get inspiration from, but I also want to point out that this is only to see through the scattering medium. So it's not inside the scattering medium. So what we try to do is get inspiration from that and apply it to our non-invasive imaging. So this is the work of Alexandra Darko and Faye Xia. So Faye is here. And we try to use this, we call this is physics-based, which it's not an invention, but that's what it's called, a two-layer neural network. So we have exactly this system. That is the imaging system that I was showing you before. So you have basically an SLM. You can basically unfold this so that the time goes from left to right and not up and down. And with this pattern, you will illuminate your object, and the fluorescence of the object will go through the medium again. So, but now it's going from left to right, and it will go to the camera. And now what you can say is you can mimic that as a two-layer neural network. You can make an analogy, some kind of model, and say, okay, now this system is basically a two-layer neural network where my first layer is the first transmission matrix with complex coefficient. Then I have my hidden layer is basically my targets. Okay, the nonlinearity of this inner layer is basically a modulus square. So it's some nonlinearity that depends on the contrast mechanism that I'm looking for. So fluorescence is a modulus square. And then my second layer is basically going through the medium back to the camera. And I have another nonlinearity on the camera. So in this case, I can actually train this network architecture. And the general idea is I don't want to train the network to do some prediction, but I want to train the network to determine the transmission matrix. So I can basically use PyTorch or whatever formalism of machine learning platform to train my neural network. And so this is, for instance, for some simulation. So with fluorescence, you can write the nonlinearity in the middle as a modulus square, and then you just sum the intensity on the camera. So there is no nonlinearity on the last layer in this case. And we could show that as we train, the loss function goes down nicely to 0. The correlation of the output goes nicely to 1. So we should be able to have the two transmission matrix in a global way like that. And it works, so we could really show that with that, just on a few beads, we could really recover the transmission matrix, and from this transmission matrix, we can refocus on one or multiple beads and reconstruct the images with this approach. So I just want to point out that this is nice, but it's not much better, at least for fluorescence, than the previous approach. NMF was just so nice and so powerful in getting rid of the noise that it didn't get much better than before. The good point is it applies to any contrast mechanism. So basically, you can apply it even when a non-negative matrix factorization cannot work. For instance, there's no positivity, for instance. And we applied it, for instance, in second harmonic generation, where now the nonlinearity is different. It's not modulus square, it's a parenthesis square, because it's a coherent process. And now there is coherent addition on the camera, so it's a modulus square for the second layer. So you can really play with your contrast mechanism, and we actually show that you just need to, depending on the coherent or incoherent and the order of the nonlinearity, you can really tackle many different modalities from Raman, linear fluorescence, two-photon fluorescence, three-photon fluorescence, second harmonic generation, third harmonic generation. So more or less, whatever your modality, you can put it in there to train your network. Okay, so conclusion so far. So I will still take 10 minutes after to speak a little bit about computing. I tried to convince you that issues are complex, but this complexity can be exploited. And shaping can undo scattering. So I was trying to walk you through the different techniques that are used, from optimization, phase conjugation, transmission matrix. Not always needed. So for instance, this autocorrelation, this phase retrieval, or this non-negative matrix factorization can help. You don't need always to do wavefront shaping. And at least for us, it was a big realization to realize that even though it's a very coherent approach to understanding the propagation, incoherent light is also okay. So fluorescence is also okay. And it's still far from being something that you can apply very quickly to in vivo situation. Even though there are some nice first demonstration, it still remains some physicist baby step, as I try to call them. Okay, so let me take a little bit of time. So maybe if there are some questions on that, I can maybe take a couple. Otherwise, I can move on to the computing and yeah. Yes. Okay, so that's 2 points. Yeah, that's a very important point. So the first question is, how many targets can I distinguish? And the answer is, it depends on how many frames you take, on the noise, etc. So experimentally, we went to about 150 that you can demix, which is not bad already. I mean, not big neurons. I mean, neurons, we didn't go to 150 because each of them has a low contrast. But individual targets, individual small bits, like diffraction-limited bits, about 150. The other question is how to determine this number. And actually, you can determine it by, because the NMF, you can basically optimize for different rank and find the one that has the minimal noise. So you can kind of find relatively smoothly the number of targets that you have in your system from your data. It's not something you need to know a priori. Okay.
Same kind of question. Your target were in one plane.
Yes.
What happens if you have targets at different depths?
Yes.
Because with an incoherent system, how can you retrieve the depth? Which is
Yeah.
something that we do with reflection matrix instead of working on this.
Yes. Yeah, that's a very good point. So what I showed was just 2D sample. Okay. So the demixing process doesn't care whether the sources are in one plane or in different plane. As long as the speckles are different, it can demix. Okay. Then the question is if two bits or two sources are in the same plane, it's just a simple shift. So if they're in different plane, then it's more complicated. You have some kind of deformation or magnification or some kind of quadratic non-uniform deformation that you need to apply to retrieve the relative position. So we are working on that quite heavily. That will be, of course, very important to go to 3D, and we'd like to do that. It's a bit tricky numerically and experimentally, but we're getting there slowly. Yeah. Oh. The number of targets you can demix. We didn't really do systematic studies of how it depends on the depth. What I can tell you is, as you go deeper and deeper, what you need to be careful about is also the bandwidth of the fluorescence. Okay, because of course the bandwidth will mean that a single target, even if it's localized, will have a lower contrast because it will be spectrally broad. Okay, so definitely as you go deeper in tissues, you will have this contrast problem from the bandwidth. You can always filter, but if you filter, you lose photons. So it's not clear whether filtering actually helps, because at the end of the day, it's just the ability of the NMF to demix, and whether it's better to be high contrast but low SNR or low contrast and high SNR is still something that we're trying to study exactly. But yeah, so it will get worse with depth for sure. Okay, let me continue a bit, and you can ask me more questions about the imaging, of course, at the end. So I try now to connect a little bit this computational approach that I was trying to glimpse at with this two-layer neural network approach to doing some computing with the with this random medium. And I want to go back a little bit and give a little bit of context. And one context is, of course, as you probably all of you are aware, is we are living the deep learning revolution. So getting to this deep neural network with billions of parameters is really revolutionizing, not just image analysis, but language models, self-driving, etc. But it become huge, humongous sizes. And each of these deep neural networks has many, many, many matrix multiplications with a huge number of parameters. You need GPU, etc. So they are extremely demanding in terms of energy and time. So one way to realize this is this, it was heuristically observed that the computing needs for deep learning is doubling every 3 months versus Moore's law doubling every 2 years. Okay, so it means that over the course of these 5 years, or no, 7 years, sorry, the need, the compute power for AI went by 300,000. Okay. At the same time, Moore's law was just doing times 7, and it's actually slowing down very strongly. Okay. So in a way, it means that having a different way to compute this matrix multiplication would be nice, and some kind of neuromorphic approach to computing would be beneficial. So there's many ways to do it, and I just want to mention that light is an interesting contender, because light is basically low consumption. You can do this interconnect very easily. It's very fast, low latency, etc. You have no dissipation like Joule. It has many disadvantages also. It's not perfect. It's much bulkier, so you need much larger structure than for electronic wires. You cannot go easily to nanometers. Non-linearities are tricky, and of course, storing photon is tough. Okay, so just a very high-level concept. But still, you have many approaches to do optical, some neuromorphic matrix multiplication and computing with light. And I think they really classify into either free space or integrated optics approaches. And there is a lot of activity recently. I just want to point out these 2 reviews from last year and the end of the year before about using optics for inference and machine learning, if you're interested in the topic. So what I want to say is that free space optics is very good for matrix multiplication. So you have all the building blocks to build this matrix multiplication optically. For instance, free space is just by Huygens Fresnel integral. You can discretize it, and it becomes a matrix multiplication, with this kind of shape. Okay, passing through a thin mask is like multiplying by a diagonal matrix, where each element of the mask is basically one element of the diagonal matrix. And so if you stack them together, so free space mask, you would get basically a combination, a multiplication of all these matrices that would result in a more dense and complicated matrix. Okay, so you can make advanced function. So for instance, if you combine propagation by some distance length, propagation by the focal distance, you get a Fourier transform. And if you now combine one Fourier transform, one mask, one Fourier transform, you have made a convolution. So you can do very easily, for instance, optical convolution with free space propagation and a mask. Something else that you can do is a so-called vector matrix multiplier, for instance, where you take basically one linear array of emitters, one linear arrays of detectors. In between, you put 2 cylindrical lenses and one 2D mask that code the matrix. And on the detectors, you can get basically the multiplication of this vector by this matrix. Okay, and you can do it incoherently, coherently. There are different schemes and so on and so forth. So the general idea is that optics is good for single-layer neural networks, but of course this deep neural network is something else. You would need nonlinearities on the way, and that's still very challenging. So what I want to show, and just briefly show you, is why a complex medium can be useful for that. Because a complex medium is basically making this matrix multiplication, where the matrix is given by the random medium. That's exactly what I was measuring before. So can you use this for computation? And the answer can be found by looking at how does this transmission matrix look like. I didn't speak too much about how it was looking like in detail. I was just showing you that it was okay. It's kind of random. But it's actually very random, and it's actually guaranteed by mesoscopic physics that there is a lot of randomness from this multiple scattering process. And you can verify this so-called Schwarzer circle law that is typical of uncorrelated random matrices. Okay. Of course, there are some, Anderson localization or long-range correlation, but you need to take a lot of care to actually see those effects. So if you don't take any care, you typically get that. And it's also very large. So you have many, many pixels on your SLM and camera, and the system itself has many, many modes that it can sustain. So it has as many modes as diffraction spots per, on the area of the system. So you typically have millions of input and output modes. So you can understand really this propagation of light through a disordered medium as a multiplication by a very large random matrix. Okay. The question is, what do you do with that? And it actually, there is a lot of work in signal processing and computer science to take advantage of this. So randomness, these random matrices, they can be somehow very good for analyzing information. And they are called actually random projections, so there's always a question of vocabulary. So once you connect what you do with the right term in this new community, you can make a lot of connection. And the correct term in computer science would be random projection. And it's kind of a universal projection. So it's really at the basis of compressed sensing for the experts. You can do dimensionality reduction like PCA, but very simply. You can do kernel method, you can do so-called extreme learning machine, randomized linear algebra, and you can even train a neural network with this random matrix. It's called direct feedback alignment. So there's many ways you can use random matrices in machine learning. And what we did in the past was really to initially to do some simple classification scheme. So it was a work with actually also Angélique, Igor Caron, Florent Zacala, and Laurent Daudet, some colleagues at the time at ESPCI, where what you do is you basically display on your SLM, which is just a binary modulator, you display images, and each image give you a speckle. And the general idea is this: you can classify as well with the speckle as with the original images. So the speckle contains some information about the original images, and two images that are similar will give speckles that are also similar or correlated. Okay, so with that you can basically do some classification, and you could show that we could get the same error on the speckle than on the original images. One interesting point is you can actually show that it's actually a bit easier because you can just do a linear regression because of this so-called kernel method that we use there. But I don't want to go too much into the details. It's interesting because you can be it can be, of course, extra large. So the matrix can be 1 million times 1 million or many million by many million. So you would need terabyte of memory to do it with a computer. You need to, bring the coefficient from the memory to the CPU and so forth. And it's also super fast. So you can do it at 10 to the 3. So it's not super fast for silicon photonic people. But if you put all these numbers together, you get about 10 to the 15 operations per second for a few watts. And this led us to create a startup, Lighton, that I won't talk about what they do today, but they do many, many things. You can buy the so-called optical processing unit that does this random projection. And I just want to take a few minutes just to show you two things that we've been doing in the lab since. One is so-called reservoir computing, which is to say that it's a way to do some, it's a recurrent neural network paradigm where the recurrent neural network has fixed weights. Okay, so and the only thing you train is the input and output layer. So this will give you some kind of mixing and diversity, and you just want to train the output layer to do some kind of prediction. And if what you do is you initialize these weights are typically chosen randomly. So when you want to look at the evolution of the system, you need to do multiplication by very large random matrices. And what we did was really just doing that with our system. So what you can do is you can show that you can encode on the SLM the input state, the input, some input time series, for instance, and the state of the reservoir. And the camera will give you the state of the reservoir at the next step, the state of the network at the next step. And with that, we did some kind of time series prediction and so on, which is quite close to state of the art and with some interesting speed up. The other thing that I would just want to flash is this Ising simulator. So we heard about Ising simulator from Emmanuel, and this is our version of it. So Ising is really this problem of finding the ground state of an Hamiltonian, where you have some coupling coefficient and some state, for instance, plus minus 1 of given spins. And of course, this is a very general problem that you can map to many machine learning problems. And what we did, and this is so Louis is here, and you can pick his brain if you want to learn more. We show that basically when you write the state of the SLM, you can say, okay, each pixel of my SLM is basically the state of my spin, and the intensity of my camera can be written as some combination through my transmission matrix, but I can basically map it to a coupling matrix. So basically, my coupling coefficients here will be linked to my transmission matrix values. Okay. So what I'm doing, when I'm focusing light, when I'm optimizing the intensity at a given point, I'm actually minimizing this Hamiltonian. Okay, so you can this way you can kind of think of an optimization experiment as actually a minimization of this Ising Hamiltonian, and we could do we could do some kind of simple proof of principle of this. Okay, so I came to my conclusion. I tried to convince you that, again, this imaging, I told you that already. I couldn't talk about everything, so I didn't mention much acousto-optics and photoacoustics, even though it's quite an active field. I didn't talk about coherent back reflection matrices, and you will see again from Alex's talks later on. I didn't talk about super resolution. I didn't talk about deep learning imaging, but there's a lot of work in using deep learning for tomography of complex media. And you can also do light field or different techniques, adapt many different imaging techniques to imaging and scattering media. In optical computing, I try to convince you that there is some interest in having this all-to-all large-scale random matrices for computing, even though they have fixed weight, so you cannot really train them, but you can still exploit them for some computing approaches. And I was just showing you two examples with reservoir computing and Ising simulator. And with that, I really want to thank again all my team and collaborators that did all the work here, and you for your attention. Thank you very much.